shown in the figure below is an RL circuit driven by an AC power source. At first glance, this problem may seem extremely familiar in that all of the steps A through F seem to be identical to those of the RC circuit of another problem. However, in part G, we're going to begin to understand how a circuit like this is useful as a filter, and we'll make a very general discussion of filters. Parts A, B, and C all deal with the process of analyzing this diagram to determine the impedance. In this case, we're going to take the vector sum of the two terms, an arrow pointed right of length R to represent the resistor, and an arrow pointed upward of length omega L to represent the inductor. The total impedance of the circuit is the vector sum of these two terms and is given by a magnitude Z and an angle which is known as the phase. We can use the Pythagorean theorem to determine the magnitude of the impedance, as shown by this expression, and we can also use the inverse of the tangent, opposite over adjacent, in order to give us the phase angle. This is a complete solution to parts A, B, and C, since we have yet to be given numbers to plug in. Part D again asks us a question regarding the impedance, and it asks us to explain in a single sentence what the phase of the impedance means. This answer is identical to the previous problem. The phase of the impedance is the phase difference between the applied voltage and the resulting current. Next, we're to plug in a few numbers into this circuit to make some calculations. We're told that the resistance is 5 kiloohms, the inductance is 3 millihenries, and that the power supply supplies a peak voltage of 10 volts at a frequency of 5 kilohertz. Now that we know these values, we would like to calculate their contributions. The impedance of the resistor is simply 5,000 ohms. However, in order to determine the impedance of the inductor, we have to perform an extra calculation of omega L, where omega is clearly 2 pi times the frequency of 5 kilohertz times the inductance L, which is 3 millihenries. Kilo times milli will cancel out, and so we're left with a very simple calculation, which rounded to 2 decimal places gives us 94.25 ohms. At this point, it's already worthwhile making a comment. The comment is that the impedance of the inductor, being less than 100 ohms, is very small compared to the impedance of the resistor, which is 5,000 ohms. As a result, this circuit acts mostly as though the inductor isn't there, meaning that the phase angle is going to be very close to that of a resistor, 0, and the amount of current is going to be nearly as large as though the resistor were the only thing in the circuit. The consequences of this disparity and the manner by which that makes this circuit a filter is discussed at the end of the problem. For now, we'll continue onward and calculate the total impedance, which rounding to 2 decimal places is 5,000.89 ohms, just as we expected, very little difference from simply having a resistor alone. However, let's not be too hasty. The total impedance was not the destination calculation of this portion of the problem. Rather, we are to determine the peak current through the circuit. And what we know is that I total is going to be equal to V total divided by Z total. This expression, which implies that I am considering both magnitude and phase, can be simplified just to the magnitude calculation, which is an identical expression. We recognize that this expression will be correct if both the current and voltage are expressed as peak, or if both the current and the voltage are expressed as RMS. Since we're given a peak voltage and asked to calculate a peak current, we're not going to have a necessity to deal with the square root of 2. With a peak applied voltage of 10 volts and a total impedance of 5,000.89 ohms, we'll get a result here expressed as milliamps of 1.9996 milliamps. If the inductor were not there at all, we would have gotten 2.0 milliamps, and so you can see once again that this circuit acts very close to not having an inductor at all. As our final calculation, before we move on to the deep considerations of the implications of this circuit, we're asked to determine the peak voltage across the inductor. Well, for any circuit element, the voltage across that circuit element is equal to the current through that circuit element times the impedance of that circuit element. Because we have formulated a series circuit, the current through the resistor and the current through the inductor are the same as each other and are the same as the total current through the entire circuit. This expression of full quantities that contain both magnitude and phase can be broken down into the portion concerning only the magnitudes, and we recognize that this expression will be correct if both the voltage and current are expressed as peak, or if both the voltage and the current are expressed as RMS. We've determined the peak current, and we're asked for the peak voltage, so we won't need to deal with a square root of 2 in this problem. We'll take our peak current and multiply only by the impedance of the inductor, since we're looking for the voltage on the inductor, and this produces the result 0.188 volts across the inductor. Out of a peak of 10 volts applied to this circuit, our friend the inductor received almost none of that voltage. Having a peak voltage 0.2 volts, that is more than a factor of 50 below the peak voltage applied to the circuit. And this is the point of our calculation as we move on to part G. In part G, we are asked if the voltage across the inductor is used to power another circuit, would this system be considered a high-pass or a low-pass filter? And then we're asked to explain. What we see clearly is that only a tiny fraction of the applied voltage would be delivered through this filter because V sub L is so much smaller than V peak. Let's ask ourselves why. And the reason was that since omega L was much, much less than the resistance, this had the eventual consequence that the voltage across the inductor was much, much less than the voltage across the resistor. We notice that although the resistance is simply a constant, the impedance of the inductor depends upon frequency. And it is this facet of the inductor being a so-called active circuit element that allows the circuit we have to be considered as a filter. Let's take a few limiting cases. If we first consider a very high frequency, we can recognize that the frequency can be made so high that omega L will exceed R by a very significant amount. In this case, V sub L will exceed V sub R, and effectively the inductor wins. On the other hand, if we had a very low frequency, then omega L would be much, much less than R, similar to the problem at hand. V sub L would be much, much less than V sub R, and the resistor would win in the sense that most of the applied voltage would appear across the resistor. That's the case in the one that we considered because the frequency was so low. How can we summarize the consequence of these two observations? If a second circuit is powered across the inductor, then the second circuit will receive significant voltage only if the frequency is high, and therefore we call this a high-pass filter. If, on the other hand, the second circuit were powered across a resistor, this same circuit could then be considered as a low-pass filter. For the problem at hand, since we have been told to power the second circuit across the inductor, the answer will be high pass. Nonetheless, we are able to generalize to rules that you can remember in future applications of filtered circuits. If you are in parallel with a capacitor, this will in general lead to a low-pass filter. If you are in parallel with an inductor, this will in general lead to a high-pass filter. And if you are in parallel with a resistor, then what you get are leftovers. The leftovers in an RL circuit are low frequencies, and so the resistor would be low. The leftovers in an RC circuit, since the capacitor is low pass, are the high frequencies. So in parallel with the resistor for an RC circuit is a high pass filter. And the final condition is, what if you have an R, an L, and a C? The low frequencies go to the capacitor, the high frequencies go to the inductor, and the resistor is left with only one frequency. And that is the frequency at which the capacitor and the inductor cancel one another. Omega L is 1 over omega C, and that is known as the resonant frequency of the circuit. And so hopefully this problem has, as its main consequence, taught us about how to recognize what kind of filter is what.